Welcome 2100. What we are doing is the conservation of angular momentum today, and this is the equipment that we'll be using, and it is a straightforward lab and very fun to do. Let me say a couple of things before we get started. One is that there are, well, as you've read in your lab manual that you fully understand right now, there are three different parts to this experiment. Or three different parts to this lab, I should say, because technically speaking, only one of those parts is the actual experiment. The two other parts are done simply so that we could obtain a measurement that is going to be used to make some calculations for a parameter that we will need in our analysis. So again, three parts. One part is the experiment, the two other parts are the measurements, and let's talk about what those three different parts are. Well, let me go ahead and just talk about the actual experiment first. So this here is going to be set in motion, and we could do that simply just by spinning it like that. And these two masses can slide on these arms. Now, right now, they are tied together with this string, and during the experiment, what we would do is get this spinning and then cut this string here. By the way, I'm not going to do it with scissors. I'm going to do it in a more predictable fashion, because the law of conservation of energy, of course, all hinges on the fact that there are no external torques applied to this system. So if I accidentally hit this, or I don't cut the string like instantaneously, I'm inadvertently introducing an outside torque. You know, the string's gonna hit these scissors and kind of slow it down. What we'll do is use a lighter, so we'll just burn it. So we are not touching this as it spins, introducing no external torques. And we burn the string. These masses, of course, will shoot outwards, and it will continue to spin. What theory predicts is that the angular momentum at any given time is always the same. So we are going to measure the angular momentum at two different particular points. One is right before I snap or burn the string, and the second point of interest is as soon as these masses slide out and hit the ends. How do we determine the angular velocity of this? Well, with this instrument right here, this is a photo gate, and just imagine a laser going from one end to the other, and there is a wheel here, and on this wheel there are spokes. So what the photo gate does is interrupted whenever it sees a spoke, and see that light? Whenever I put my hand in between, the light goes on. So it knows how fast this wheel is spinning, and because the program knows how many spokes there are, it could determine the angular velocity that this thing is spinning. So that's how we determine the angular velocity, and of course all we do is just look at a graph. So we don't have to like plot these by hand or make any calculations, so it's very easy. Let's see. Unfortunately, friction isn't totally negligible. With our air tracks, it's negligible to a good approximation. But with this, it's not. There are bearings. They are quite old. I bought new ones. Unfortunately, I didn't have a chance to replace them all. It isn't as simple. It's not even made to. Anyway, these bearings do produce friction, and friction in this equipment here, it turns out that it is a function of how fast this is spinning. So when this is spinning super fast, it's like initially when we get it in motion, when I let go, when I'm no longer touching it and applying an external torque on our system, theoretically, the angular velocity should be constant, right? If we were to look at our graph, we should just have a straight line. You'll notice when you see your graph, though, that it is going to dip significantly. And again, that's just because of friction. Cut the string, these slide out, and as these are sliding out, the moment of inertia is constantly changing. The time it takes for these to move from here to there is like a split second. So within a short time interval, your graph is going to jump down, and then it's going to level off because it'll be spinning at a slower angular velocity. Now, when you look at the curve at that smaller angular velocity, it isn't going to be dipping down as much as the initial part of the curve, and that's because it's moving slower. When it's moving slower, for whatever reason, like I said, friction is a function of its speed. When it's moving slower, friction doesn't play as critical a role. So the bottom part of your graph is going to be relatively level. You could tell that it'll be losing and energy just slightly, and in effect angular momentum, but just a tiny bit. But anyway, when you do your analysis, I put some comments next to those graphs, or I will put comments just to help you get the best data and in effect analysis that you could possibly get. Normally when I do one of these labs, I'm shooting for like 1 or 2% air. With this equipment here, doing this prior to swapping out all the ball bearings in here, we're gonna shoot for, let's just get under 10%, and I think we'll be good. Let's see, so that is our actual experiment. Now, what are the other two parts? Well, first just let me say, if we wanted to determine the angular momentum of this here, we would need two things. One would be its angular velocity, and that's going to be easy to obtain. Our software is just going to spit that out, or it's going to make a graph, and we could easily determine the angular velocity just by looking at the graph. But we also need its moment of inertia. So technically, we could calculate its moment of inertia. Moment of inertia is nothing more than what mr squared. We'd have to take the integral, though. That would be a horrible exercise to do this mathematically, because we'd have to integrate over this whole thing. If these were spherical, maybe we could model them as point masses, but they're cylindrical, and then there's this here, and even these hooks, it'd be horrible. We can do away with all the mathematics, though, by a different method, and that method, of course, is outlined in your lab manual. What we are going to do ultimately is simply apply a known force to the edge of this shaft, thereby imparting a known torque, right? That will get this spinning. So with that known torque applied to that shaft, it will produce constant angular acceleration. So if we know the constant angular acceleration, we could then determine its moment of inertia. And there's an expression for this in your lab manual, and it's totally derived for you, so there's no mystery behind it. It'd be advantageous for you to fully understand it, though, how it was derived. So with those simple measurements, which would be, let's see, what do we need? We need the diameter of this shaft. So I'll give that to you. Actually, what I'll do is I'll use a pair of vernier calipers, and measure the diameter. Normally I would supply you with a photograph of the vernier calipers and let you read it, but I'll just give it to you. So you need that to determine the torque. And let's see, and we need the constant applied force at the edge of the shaft. That's going to be easy to determine. What we do is use this. This is a 100-gram mass. I'm simply going to tie it to the end of the string, put it up against this, put it over this pulley, and wrap it around this shaft. Release it, and it is going to apply a force at the edge of that shaft, producing a torque. And what is the force that is causing that torque? mg, right? Basic. So those two parts that I spoke about that aren't the actual experiment, just part of the lab that is used to do some measurements, well, that would be one of them. And what is the other one? We need the moment of inertia for this system for two particular points. One will be for this configuration here. So I tie this, wrap it around, set it in motion, record its angular acceleration. Then I compress these, tie them together, get this, hang it, wrap it around, let it go, imparting that external torque, get this spinning. There's going to be an angular acceleration. Our software will pick that up, which will enable us to determine the moment of inertia for this configuration. So after we have those two bits of information, the moment of inertia for our initial configuration and the moment of inertia for our final configuration, we can just go ahead and do the experiment. Spin it, burn it, measure the angular acceleration for before. Well, it's going to measure the angular acceleration for the whole process, but we're going to pick out what the speed was just prior to cutting the string and just after we cut the string. Well, how much just after we cut the string? We cut the string. Okay, here's this in slow motion. We cut the string and this moves out. It's spinning and this is moving out, moving out. We need to be sure to pick the point right when this hits the end. I mean, of course, after it hits the end, it's going to continue to spin. And as I mentioned before, it loses speed very, very slowly when it's traveling slow. So I guess it's not that important to pinpoint the particular time when this strikes the ends. But that's what I would do if I were you. I would try and pinpoint that time. In fact, there's one question in the analysis, I think it's question number 4, where it asks you to determine how quickly this is accelerating. Well, it's going to have a negative value, right? Because it's getting smaller, the acceleration. Between the time of this and this. And to determine that, you will indeed need to know the particular time when these hit the end. But anyway, that'll be provided to you in the form of graphs and a data table. So it's all going to be easy. This is easy stuff. We're good to go. Let me put you on pause. I am going to, let's see, what am I going to do? Let me tie it up. Let me tie it up and we'll get underway. Okay, hold on. Okay, so I have everything set up for the part where we apply a constant force and get this thing spinning and determine its angular acceleration. And again, this isn't the actual experiment. This is just done so that we can determine the moment of inertia. All right. So my system right now is collecting data. Don't worry, I'm going to just give you the data of interest. In other words, when I release this weight and get it spinning. So here we go. It's getting faster and faster and faster. Obviously, there is a certain angular acceleration. Okay, so that's all I need. Let me turn off the software. If you noticed anything funky happening, like it was getting faster and faster and faster, and then it stopped getting faster and started doing something weird, that was just because the weight that I had on the end of this string touched the ground. So it stopped applying a constant force, and then this of course started wrapping around the shaft in the other direction. Doesn't matter. So I have a bunch of data collected, and I'm going to just give you like the first 20 seconds, where like right when I release the weight on the other end of this pulley to right before it hit the ground. And by the way, you might be wondering, how did I wrap this around the shaft and the string not slip? There's just a little piece of beeswax on that shaft, so it kind of like it holds it in place. Anyway, let's get on to part 2. Actually, wait a minute. Okay. The second part, we need to do this all over again, right? But with these masses out here to determine the moment of inertia of the system where these masses are fully extended. But instead of doing that, how about we just go ahead and do the experiment now? And the reason I say that is because this is already tied together. So, you know, I'd have to cut this, move those out, do that whole thing, and then bring them back together and tie them again. Plus, this would need to be tied so that they're compressed in exactly the same position. Well, they're just about buttered up. If there was a little bit of play, it'd be hard to reproduce. But anyway, I don't want to have to retie them. So let's just go ahead and do the experiment right now. And let me get my lighter, which I don't have. Actually, I have crap. When we do this, we use a fireplace lighter, right? I have this little lighter. I guess I could do it with this. Nah, this is going to be too difficult. I'll put you on pause and get the other lighter. Hold on. All right, ladies and gentlemen, I have my lighter here, and the software is on. It is collecting data, so all we need to do is get this thing in motion and cut this string. So let's go. Get it spinning a little bit faster. All right. So I will give you probably like 3 seconds of data before I cut it, and maybe 3 or 4 seconds of data after I cut it. Okay, right now I just shut off the software, so it's not recording anymore. But essentially, that was our experiment. And obviously, the moment of inertia of this system when it's configured this way is much larger than when these masses are tied together. In other words, let's see, it'd be harder to get it spinning. It would take more effort to get it spinning when it's like this rather than when these two are tied together. And of course, you already know this, right? Need I bring up the tired example of a figure skater with their arms stretched? Okay, so let me put you on pause and set this up so we could do the last part to get that last measurement we'll need to determine the moment of inertia for this configuration. Hold on. Okay, we are now set up to take that last measurement, and as I mentioned before, the moment of inertia with this configuration is much larger than the initial configuration, and you'll see because I'm going to apply the same amount of force that produces that torque to get it moving as I did in the first case. But right now you'll see that it spins much slower. And just to convince yourselves, remember mathematically or by definition, what is moment of inertia? M times r squared, where r is the distance between the mass we're considering and the axis of rotation. When these masses were together, the distance from the mass to the center is rather small. So that's your r squared. That was the moment of inertia contributed by these two masses, so it'd be twice that. Now in this configuration, it's the same mass, right? But what is that r? It's from here to here. It's a large r that's going to be squared. So the moment of inertia dramatically increases. And let us get this in motion. Now I'm already taking data. It's our software is acquiring the data right now, but again, I won't give that to you. I mean, it's worthless, right? I'm just setting this up. I will just give you the data of interest. In other words, from the moment I take my finger off to right before this weight touches the floor. So here we go. Again, this is the same external torque applied to this as we did in the first case, and look at how slow it's going. It's much heavier, for a lack of a better word. The moment of inertia is greater, and it just slipped off the pulley, but it doesn't matter. Let me just turn off the software. I wasn't watching it. I don't know how it slipped off the pulley, but it doesn't matter. We have plenty of data from the moment I released it to way before it slipped off. We could use that, and we're all good. I will get these graphs for you. I'll make comments with those graphs. I'll give you a table with some data, and you can have at it. So I'm wondering, let's see. I'm wondering if I should say see you next week. I'm thinking like, wait a minute, is this our last one together? But yeah, there is another one. So as always, I'll see you next week.